Welcome to the 4th Annual Center for Biomedical Sciences and Engineering Senior Recognition event. Throughout the past 4 years, students within our program have learned about a variety of biomedical sciences and engineering topics and did many hands-on labs to prepare them for life beyond the walls of Coon Rapids High School. Students, we are incredibly proud of your accomplishments over the past 4 years. We are confident the Biomedical Sciences and Engineering program has prepared you for your future success. Thank you to Anoka Hennepin School District, Northwest Suburban Integration School District, the community, and Project Lead the Way for their continued support of the Biomedical Sciences and Engineering program at Coon Rapids High School. It is because of you that we have been able to establish a unique program to prepare our students for college and careers within the biomedical sciences and engineering fields. To begin, we would like to welcome our guest speaker, Wade Demmer. Wade is an active parent of the Coon Rapids school community. He serves on the Coon Rapids City Council, and he is an innovative director at Medtronic. He has played an integral part in the development of our program through being a mentor to our students, being a member on our industry advisory board, and welcoming us into Medtronic so students can see how the concepts they are learning apply to real life.
Hello, Coon Rapids High School Center for Biomedical Sciences and Engineering, Class of 2020. Congratulations on your graduation. I want to talk a little bit about the future, and I don't mean next summer or summer after that. I want to talk about the year 2050. I figure by around 2050, something that might be happening for you is that you'll be sitting down and you'll get a holographic call from a grandkid who wants to understand what was going on during the pandemic of 2020. It's going to be an interesting conversation for you to have because the world will have changed by so much, and you're going to have to sit back and try to explain how things changed the way they did over that time period. You're very likely to start off by talking about how the start of your senior year went, how you were involved in this program that's an integrative program that tries to teach you how things are connected, how the biomedical sciences are connected to the rest of your high school curriculum. You're going to talk about what your expectations were going into that school year and how so many things changed. And you're going to talk about how the world changed afterward as well, and that's what I want to talk to you about. You've been part of this integrative program now for several of you for 4 years, where you've understood things that a lot of us are just starting to understand as adults. You get to see how to think of things as a connected system. And I've been able to watch this. I've seen your program, I've seen your class projects and how you guys are able to take a problem, understand the problem, try to break it down into solutions, and understand that you can't do it by just knowing one thing. We see the world now as much more connected than we might have thought just a little while ago. You understand that public health, biomedical sciences, the economy, supply chains, feeding people, globalization, all these things are connected. And the math and sciences that you learn in school are the weapons that you use to understand some of these connected things. Most of us didn't think those things were connected in the way that they are. And what's going to happen, I think, going forward for you is that early understanding and that seeing what the world is like is going to change the way you think about problems. It's very common in a city to think about the 100-year flood. We don't build buildings in the 100-year floodplain. You're going to be thinking about the 100-year pandemic for the rest of your life. Things are going to swing. Things are going to become overreact. Things are going to underreact. Things are going to overreact for a while and then underreact for a while after that. People aren't going to understand 40 years from now why they should do the things that we put in place after this pandemic. But you'll understand. You'll understand how these things are connected and how pulling on one thread affects the rest of the sweater. It's really exciting for me to see your generation get this kind of head start in leading. And I don't mean to make it sound like the next couple years are going to be easy, because you're going to have struggles. Everyone is going to have some challenges as you grow up and move through the world. But you have this head start that most of us never had. Now, your class is unique. Your class is a class that made sacrifices, and while some people might think the sacrifices of losing prom or losing the end of your senior year aren't a really big deal, I challenge that. I think that's wrong. A lot of us are able to look back at our past and we remember the end of our senior year very fondly. What you have, though, is you sacrificed those lifelong memories for a different lifelong memory, and that different lifelong memory is that you gave up those things so that people could spend more time with their grandparents, so that as a society we didn't have the potential catastrophic effects that people worried about. You spent the last couple of months in a very unique situation. The class before you didn't have that situation, and hopefully the class after you won't either. You're going to be held together by this bond that the class of 2020 went through something that other people didn't. And you, as biomedical sciences students, understand it better than most. It's been wonderful to watch how clever you've been in your solutions. It's been wonderful to watch how you've been able to tie things together, and it gives me a lot of hope that this class and this generation has future leaders that will make sure these things are tied together in a way that optimizes for all of society. That's a big ask, and I'm not saying you have to do it tomorrow. But we're talking about the year 2050 here, and by then I think you'll have made enough changes to the world that it'll be very, very difficult to explain to that grandchild what it was like in 2019. I hope that you go forward with the hope and positivity that the things you've learned here in Coon Rapids set you up well for a different future than what you expected, because quite frankly, none of us get the future we expect. I hope that you take pride in the things you were able to do in school, that you got the opportunity to do that so many other people would have never been able to do. I hope you understand the head start that you have in learning how interdisciplinary studies make a big difference. I hope that you find that this work that you did is meaningful, and I hope that you all have wonderful and bright futures, because I do believe you are all capable of it. I've been so impressed with the things that you've done, and I just want to wish you the very best as you go forward into the future. Congratulations on your graduation. Thank you for the sacrifices that you've made, and I really do believe that your leadership is going to be a critical part of the country and the world's future. Good luck.
Thank you, Wade. We appreciate all you do for our program and for providing an uplifting message to our seniors. Next, many of our senior biomedical sciences students participated in the Biomedical Innovation capstone course, where they built on the knowledge and skills they gained within our program to design innovative solutions to healthcare challenges of the 21st century. Next year, we are excited to add our engineering students into the capstone course as well. A very special thank you to Mr. Luke Glidden and Mrs. Ann Glidden, the Biomedical Innovation teachers. They have spent countless hours working with our seniors as they determined their capstone project topic, gathered data, and compiled results into the presentations you're about to see. You both are amazing, and our students appreciate you so much. After we hear from them in a minute, there will be a series of 10 capstone presentations. For each group, we will begin by highlighting each student, and then they will give their presentation. The video will transition from one group to the next. After that, we will highlight all of the seniors who were not in the capstone class this year. Also, be sure to stay tuned till the very end of our virtual event for some farewell messages from our administration and some of your teachers, and there's a couple of tiny guests in there too. Now, here are the Gliddens to talk about the senior capstone course.
Hi everyone, we're Anne and Luke Glidden, and we teach Biomedical Innovations, which is our senior capstone course in the Biomedical Sciences program. In our class, students work in groups to design and conduct a research project or experiment in an area of science that is interesting to them. Each group also works with a professional mentor who's an expert in their chosen field of study.
So in addition to learning about the science behind their project, students also learn professional skills through collaborating with their group, communicating with their mentor, presenting their findings, and developing their resumes and interview skills. In February, our students had the tremendous opportunity to present their capstone project work to a group of scientists and engineers from Medtronic. We're grateful to our community volunteers who have been guests in our classroom, attended our students' presentations, and given students feedback on their resumes.
At the beginning of the class, when students are choosing a capstone project, they're often concerned, will I be able to finish this project in time? And while we encourage students to plan a realistic project, we also know that science rarely goes as planned, and we can learn from whatever results come our way. And that's certainly proving to be the case this school year. So while we'd love to be able to show you the students' work on their projects in person, we're also so impressed with their resilience as they go through so many changes during this time. We are so proud of them and of the work they have done this year, and I think their growth will still be evident in their presentations that you'll see virtually tonight.
Hi, my name is Sarah Abbas, and my capstone group and I conducted our project on contrast bone cement. So our story actually starts with our mentor, Mrs. Zainab Abdul Hadi, and she is a surgical support systems coordinator at Abbott Northwestern Hospital. Essentially, she works with the sterilization of medical instruments. We got to visit her in the hospital, as you can see on the pictures on the right. She opened us up to the sterilization of the medical world, and we found that it was really important that instruments are sterile. The CDC reports that there are 687,000 cases in the US yearly, and it results from having unclean tools. This is an alarming problem. We wanted our project to look at current sterilization procedures and see if there's anything that we could change and make more effective. As we dove into the sterilization process, our team found that sterilization technicians had a hard time with orthopedic tools because of this thing called bone cement. Orthopedic surgeries would need bone cement to repair things like hips and knees, and it's a material that's sticky and hard to see, so it's a lot harder to clean off. Bone cement causes sterilization procedures to become more inefficient, so we decided to narrow our project's focus on that. In formulating our project goal, we first looked at the current research being done. Contrast bone cement, which is dyed bone cement, was being used so both surgeons and technicians could see the cement much easier. Contrast bone cement is what is being used to solve this bone cement problem. Our capstone group then decided to further research contrast bone cement because it turns out that current contrast bone cement uses something called methylene blue dye, and this actually negatively impacts bone cement attributes like its mechanical ability and flexibility. So our goal was then to develop a new bone cement that could help make sterilization easier without harming the bone cement attributes. After much research, our group came across the dye methyl blue. We wanted to research this dye and answer the following questions. Can we use methyl blue dye to create a contrast bone cement? Like, will it even work? And would this new dye be a better contrast bone cement than its predecessor? In coming up with the actual experiment, our team reached out to Professor Conrado Aparicio at the University of Minnesota Twin Cities. The professor helped us come up with a way to make samples for our trials, which was then creating molds for bone cement. Using these samples, we could then conduct the following tests: setting time, mechanical ability, and flexibility. That way, we could see if our proposed dye was actually better than the original dye. Sadly, we weren't able to conduct the experiment due to the COVID-19 pandemic. The big picture for our capstone project was to create a contrast bone cement, something that would aid both surgeons and sterilization technicians. It's so important to make sterilization procedures as effective as possible so patients are not harmed. With this project, we learned a lot. Our capstone group got to understand how important sterilization is. We got to use 3D printers and make sample molds. But best of all, we got to build problem-solving skills together as a team. These wonderful experiences can help our future careers into medicine. Our capstone project couldn't have happened without the efforts of our mentor, Zainab Abdul Hadi, Professor Conrado Aparicio, our advisors, Mr. and Mrs. Glidden, and STARS Labs. Thank you for listening.
Hello, this is Masuma Sayeda. My group members are Amina Atia, Pearl Jensen, and Vanessa Santana. Our capstone research project was on manganese oxidizing bacteria. However, we didn't select this topic when we started our capstone project. Our very first idea in early November was to study how different preservatives in bread affect mold growth. But once we completed basic research, we realized we wanted to work with microbes instead. So we looked for a mentor who is specialized in biology. Through our research, we found Mr. Su, a PhD graduate student at the University of Minnesota. After contacting him, we found out that he studied MN oxidizing bacteria. We then did research again and found out the bacteria could possibly be used to remove manganese from drinking water and cleaning it in the process. Once we had our project idea, the final piece was deciding on a specific bacterial strain that we could work with. With the help of Mr. Su, we chose Pseudomonas potida GB1 because of its ability to oxidize manganese. In the end, we completed a summary of a review paper and a grant proposal. After we decided our project topic on MN oxidizing bacteria, we developed a research question. Throughout the whole experiment, our goal was to find an efficient way to remove manganese from water using bacteria. To achieve our goal, we did further research and read through scientific papers to find effective methods. In simple words, our method consisted of introducing the bacteria that we would keep alive in Lb-rich media agar plates into water contaminated with manganese. In theory, the manganese would oxidize and transform into a solid. Then the solid would be manually removed with a coffee filter, and the water would be rid of manganese. After that, our idea was to filter out the bacteria with micron filters and clean water would be produced. To minimize human errors in our experiment, we had dry runs. The top three pictures shows manganese testing. We used this test to make sure if our method of removing the manganese from water was successful. We used manganese testing sticks to wet in the manganese contaminated water. Then we compared the sticks color to the given chart. It showed not only confirmed presence of manganese but also the amount of it in the water. The top right corner picture shows the testing of microfilter. The top right picture shows the dry run of cleaning water from bacteria after manganese is removed. This syringe is filled with bacterial water injected into a 0.22 micron filter. This filters out the bacteria and produces the cleaned water. The bottom images shows the process of making algae-rich media plates to keep the bacteria alive. The bottom right image just shows one of the many chemicals used to make the mixture, and then it being dissolved in water. And finally, we are making a whole mixture with many other chemicals and pouring it in the Petri plates before storing it away to use a letter to keep the bacteria alive. Even though we have not conducted the actual experiment or concluded our project, but up to this point we have gained many skills and learned a lot as a group. In the end, we learned numerous skills that can help us succeed later in life. We gained research abilities, learned how to function as a group, and improved problem solving. We've also become better at communicating with outside help, such as our mentors, instructors, and professionals in the field. This project has also helped us explore our interests. We learned that studying the growth of mold does not interest us. In general, we also saw firsthand the amount of work that goes into conducting the whole experiment. This learning will help us prepare for undergraduate research, which can be beneficial for careers or graduate school, or both. Thank you for your time and listening about our capstone project on manganese oxidizing bacteria.
Hello, my name is Kothar and my group members are Arya, Arlisa, and Christina, and our capstone project is on HPV detection. HPV stands for human papillomavirus. It's the most common sexually transmitted infection. HPV is usually harmless and goes away by itself, but some types can lead to cancer or genital warts. We chose our project because current HPV diagnosis methods are invasive and creates a stigma for getting tested. Having a more efficient, low-cost screening method would help diagnose people of low income and people in places with fewer healthcare resources on a wider scale. People are also able to do so in the comfort of their own homes. So for our project, our mentor was Dr. Janet Beneke, who is a specialist in pathology. The main aim of our research was to find a way to better isolate cell-free DNA from stimulated urine and figuring out which silica source, magnetic beads, sand, or mini columns would yield the most and highest concentration of DNA. For our procedure, we mixed diluted stock DNA with stimulated urine. We added sodium acetate alcohol to the silica source to absorb DNA. We then washed the silica material with ethanol and released the DNA from silica using tris buffer. This then quantified our DNA. We did the majority of our work in the BI room at Coon Rapids High School. For our experiment, the variables were the silica-coated magnetic beads, the silica mini columns, and the silica sand. The outcome was the total concentration of DNA extracted. For our preliminary trials, we didn't get any results as the bands didn't appear on our gel. For example, if you look at the top picture, that was our first gel that we made, and as you can see, there are no bands appearing on that gel. This then caused us to do some trial and error and make some modifications to our samples. So the modifications that we made were that we used more red stain and buffer in the DNA sample. We also changed the concentration of our thymus DNA. Even though we made some modifications, it still resulted in none of the bands appearing on the gel. In the end, we were able to figure out that the UV fluorescent dye didn't show up on our gel box, but it did work on Ralph, who was our mentor, that tried at Augsburg University. This made us believe that the boxes must have different light wavelengths. What we learned was that the process of researching is very long and can be challenging, especially when the topic you're researching isn't very popular, but it did teach us patience and that you know that all the work you're putting in will pay off in the end. We also learned how to manage disappointment and how to reflect. We learned that things won't always turn out the way you expect them to, and that's okay. It's helpful to look back at these mistakes to prevent repeating them in the future. We also learned how important it is to reflect. Reflecting off of things we did prior, such as past presentations or trial runs, helped us to learn and build off these mistakes to do better next time. We would like to acknowledge our mentors, Dr. Janet Beneke and Dr. Ralph Butowski, as well as our amazing teachers, Mr. and Mrs. Glidden, for always being there to help us. We really appreciate it. Thanks for listening.
This is Plant Epigenetics by Abby Ellenbecker, Meredith Foster, and Kalia Jones. For our project, we wanted to determine how the environment affects the expression of the anthocyanin gene in Wisconsin fast plants and whether or not epigenetic changes in anthocyanin production are heritable. Wisconsin fast plants were made by the University of Wisconsin-Madison, and their short life cycles and easy-to-grow nature make them perfect candidates for studying genetics. We used the purple stem hairy breed of Wisconsin fast plants because they contain a purple pigment called anthocyanin. We were going to grow our plants in different environments to try and influence the amount of anthocyanin produced in the plants. Anthocyanins act as an antioxidant in the body and are beneficial to bodily health. We care about
this because if we can manipulate anthocyanin production on a small scale, it could help us find new tools in food science on a larger scale. In order to test our hypothesis, we plan to grow 20 plants in 4 different environments: a control with 24 hours of light at approximately 65 degrees Fahrenheit, a low light environment with 12 hours of light per day, a high temperature environment at 80 degrees, and a low temperature environment at 40 degrees. After plants in each environment had grown for 2 weeks, we would extract pigment from the stems of the plants and measure the absorptivity. This would tell us whether or not the pigment gene expression was affected by the different conditions. If we were able to identify a statistically significant difference in the pigment levels of the plants grown in the different environments, then our next step would have been to pollinate the remaining plants. This would produce seeds, which we could have harvested and used to grow a second generation of plants that we would have grown in control conditions. After growing for 2 weeks, we would repeat our previous methods to compare pigment levels. If there was a difference in the pigment levels in the second generation plants, this would have told us that the epigenetic changes we had induced in the parent generation were inherited in a second generation, and we could confirm that this change was indeed an epigenetic one. The absorptivity of the greenhouse or high temperature plant stems and the control plant stems revealed that the control plants had the higher purple pigmentation than the high temperature plants, although this could have been because of the quality of the plants. The control plants were fully grown and much healthier than the greenhouse plants. This factor could have led to better results with the control plants than the greenhouse plants. Therefore, our results are unclear whether the epigenetics of the plants changed the absorptivity levels, or how well the plants were able to germinate determined the pigmentation levels. Due to the unexpected shortened school year, this step was the furthest we could go in our procedure. Although our capstone project did not go as planned, we learned a lot from our experiment. Going into our experiment, none of us knew anything about epigenetics, the study of changes in an organism caused by gene expression. To change the epigenetics of a plant, we found out that the environment of a plant must be changed. This could either be done by soil or temperature change. Throughout the experiment, there were several trials and errors. For example, at one point, the plants weren't even growing at all. Overall, we learned that the experiment was not going to go as fast as we planned it to. Our group had to understand that we might not get the results we planned to receive, for it is our first time putting on as big of an experiment as this one. In the end, none of this would have happened or been possible without our mentor from Augsburg University, Dr. Leon van Eck. He really helped us to understand what we were doing and gave us a big start on our project. Mr. and Mrs. Glidden also played a huge part in our experiment. We would not have received the positive results from our experiment without them.
Hello, I'm Rachel Dieters, and my group's project was a public health campaign against vaping, highlighting the effects it has on the body as well as how to prevent this unwanted behavior. The original plan was to test lung tissue samples of vaping usage versus non-usage. However, we ran into issues with how we were going to get the vaping chemicals into the lung tissue. We then turned to researching what a public health campaign was and what they were comprised of. Through this research, we found Dr. Ilako Vaughn, who is a George Washington School of Health graduate. She helped us in planning the campaign and different outreach methods. For our outreach plans, we created a tentative timeline for our campaign that began in late March and ended in early April. to avoid big events such as prom and spring break. Phase 2 of the project was to utilize the teachers in the building to create the most effective outreach methods possible for our campaign. The question that started it all was, what are the most effective ways to educate students of the dangers that vaping nicotine and THC cartridges holds, and how do we prevent these behaviors? So our goal of the whole campaign is to prevent the student body from vaping both nicotine and THC cartridges by exposing them to different outreach methods that we researched. We used multiple surveys for gathering data. Most of the data we used came from the Minnesota Department of Health district surveys. But we did conduct a survey that was taken by students during core. These surveys helped us to get an idea of the behaviors and methods students use to get their vaping products. We also read multiple papers on THC and tobacco use, as well as a vaping study that was conducted to measure lung damage. From the campaign, we have learned vaping has become a serious issue in the student body, as well as how young kids start vaping and how they get their vaping products, as well as how hard it is to get reliable data from surveys. As a group, we would love to thank everyone that was able to help us in this project, so thank you to our experts, teachers, staff, students, and everyone else that has helped. So thank you.
My name is Katie No, and me, Dola Adamola Green, Zainab Al-Obeidi, and Caitlin Goldman worked on our project titled The Electroporation of Antibiotic-Resistant Bacteria. This project started when we came across this article about electrochemical therapy being used to treat infections on implants. We were intrigued by the idea of using electrical pulses to allow molecules to enter a cell. Being that antibiotic-resistant bacteria is a large issue in the medical field, we brainstormed how we could apply the use of electrical pulses to this issue. Mr. Glidden helped us narrow down our research ideas and guided us towards electroporation. This is where we found an article written by Dr. Shao, who later became our mentor, about his research using electroporation. We learned more about the biological side of our experiment from our other mentor, Dr. Irina Makarevich. Through our group conversations amongst ourselves and our mentors, we finalized our research question. Will electroporation effectively make bacteria more susceptible to antibiotics? This figure shows how bacteria becomes resistant to antibiotics. The first image shows bacteria before treatment, and the middle one shows it after. The green bacteria starts to multiply because it is resistant to the antibiotics, while the purple dies after treatment. We plan to use electroporation to shock the resistant bacteria, opening up pores in the cell membrane. This would allow the antibiotic that the bacteria is resistant to enter the cell and theoretically kill it. For our experiment, we are working with two types of E. coli, one that is resistant to streptomycin and another that is resistant to ampicillin. Before we performed our experiment, we started by developing a method to count the bacteria remaining after treatment with electroporation and antibiotics. With the help of our mentors, we discussed various counting methods such as using a microscope or a spectrophotometer. However, we decided on using a serial dilution method. We decided this because it would give us the ability to count the colonies remaining on the last dilution. As you can see in the image, the most diluted plate on the far right allows you to count individual colonies. For our procedure, we would start out by making a solution of bacteria by mixing E. coli with LB broth. For our preliminary trials, we put each bacterial solution into the electroporation chamber and tested the various settings. For our experimental trials, we had planned to mix each type of bacterial solution with the respective antibiotic and place that into a cuvette, which would then go into the electroporation chamber. After electroporation was completed, we would then use a micropipette to take the solutions and place them each into their own cell well. We will then dilute each solution by a factor of 10, 6 times, and then grow each dilution on a Petri plate. We would then be able to see the growth, count the colonies, and multiply by the dilution factor to determine how much is still alive. Although we were unable to perform our experiment, we were able to obtain some results by performing our preliminary trials at the University of Minnesota, thanks to Dr. Shao. We tested 5 different voltages: 500, 750, 900, 1100, and 1300 volts, and returned to the high school to incubate and analyze our results. This image shows the growth of bacteria after it was diluted. All of our bacteria ended up looking very similar to these plates, so we concluded that for our experimental trials, we would use the voltage at 1100 volts. We came to this conclusion because it was the highest voltage possible that wouldn't kill the bacteria, as we tried 1300 volts, but the machine could not do that. We hypothesized that if the bacteria died during our experimental trials, it would be due to the antibiotics entering the cell and killing it, and not the effect of electroporation itself. Overall, even though we did not get to finish our experiment, we still learned a lot along the way. We experienced many trial and error scenarios that were not mentioned previously. As a team, we learned how to work through that and continue to push forward. When we first started, we were unsure that we would be able to get such remarkable professionals to collaborate with us. But we executed professionalism, and we were able to connect with our 2 mentors. We would not have made it to the point that we did without the help of our mentors, Dr. Shao and Dr. Makarevich, and all of the biomed teachers that we have had over the years. We are so grateful for all of you and what you have taught us. Thank you.
Hello, welcome to our capstone project. Alright, so first, the intro. So the reason why we're doing this project is we realize there's a lot of pollution, and now it's the biggest concern for this world. And also we search the history, and we know it's in the 1980s biodegradable were introduced, and that plastic company has spent over $1 billion trying to promote recycling. So the background. So first, biodegradable water bottle degrade in shelf. So they degrade over a period of time. But the difference between that and regular plastic is that regular plastic takes over 1,000 years to degrade, but it's more reliable. Yet it's harming our environment. Our research question is that we would like to find a way to make biodegradable water bottle viable in an environment that is suitable for selling while keeping properties. So that way, we can it actually degrades, but it's still suitable for selling. So some of my experiment plans were that we coat like the cups with wax, and we had 2 different types of wax. It was like carnauba and beeswax. We're currently like testing on those. Also, like we were trying to heat up the cup to see like the melting point and what it can take. Also, like we're just trying to find ways to coat the cup too. And overall, this is our results, and we're still continuing working on that.
Our project was medical drones. It was done by Austin Enyart, Marissa Nelson, Josiah Novak, and Eli Olson. We wanted to provide a way for bystanders to help in emergency situations. We realized also that medical drones deliver first aid kits faster than ambulances can get to a scene. This means that bystanders can start first aid before medical professionals arrive. We want to take a moment to thank our mentor, Officer Platts, for helping us to press out the details of what our question would be. So what is that question exactly? Can we turn bystanders into first responders? So the issue here is that bystanders are not medical professionals. They don't have the training to know what they're doing. However, one of the members of our group does have EMS training, so we decided to make directions that would be able to walk bystanders through the process of first aid. So our research plans. We were going to have people test our directions. We were going to give them one of the 3 of our scenarios: bleed, broken bone, or cardiac arrest. They then got the first aid supplies and 4 minutes to follow the directions that came with the supplies. They were going to be given a rubric to score the directions in several places, such as if they felt the directions made sense or if they felt they had enough time. We would then edit the directions to take into account the scores of the rubric. For example, if someone said that they were too wordy, we would make them more concise and things of that nature. Sadly, we never got to do any testing due to school closures. However, we plan to begin testing the week of March 23rd. We were planning on testing 20 people in Coon Rapids for each set of directions, and then going to edit the directions after having gotten the results, and then test directions again if we had enough time. So the big picture. Despite not being able to test, we still learned many things. Firstly, we learned how to identify a problem, which seems simple enough, but to get to a solution, your problem has to be broad enough that a solution would help people, but also specific enough that a solution does exist to solve the problem. Secondly, we learned that testing in a closed environment is significantly different than that of the real world, and we had to find ways to counter that, and make our scenarios as realistic as possible. We'd like to give a special thanks once again to Officer Platts for helping us identify our problem, to Bill Nice at Spring Lake Park High School for lending us materials that we needed for testing, and to Wade Demmer at Medtronic for helping us identify strategies to make testing more realistic. And thank you all for watching.
Hello, my name is Amaya Hill, and my group members are Amani Ba, Faith Ose, and Shania Scarborough. The experiment that we will be testing is the Good Samaritan effect. Our main focus was to deal with an experiment that dealt with people's ethical and moral behavior, otherwise known as do people know the difference between right and wrong? Our first experiment that we studied was the prisoner's dilemma. This is a game that tests whether or not people do the right things when they know they are at risk at dealing with some type of penalty. The next experiment that we were going to study was the bystander effect. This is an experiment in which we would use similar tactics as to show what would you do and see how did students react to different situations. Our current experiment is the Good Samaritan study. In this experiment, we will study the motivation behind why people do good for others. Our research question is, in a given situation when students are presented with a kindness incentive, are they more inclined to help others? We hypothesized that if students in high school are given a kindness incentive, they will show greater value on the kindness scale instead of the students who did not receive a kindness incentive. This experiment would take place in a high school setting, preferably the hallways of the high school, to create more of natural scenery. The students who will be participating in this experiment would mostly be high school students that participate in the Biomed program. Two groups that will be tested in this experiment are the control and the experimental group. Like the original study, students were told to read about what it means to be a good Samaritan. In our case, the students will be given a speech on what it means to be kind to others. The students participating in the experimental group will also be given a stuffed cardinal, which represents our school pride, and students in the control group will be given only the speech. We would have selected different actors to play out one of the 3 different scenarios and test the students' involvement. We made a scale from 0 to 2, 0 being the students completely ignoring the situation, 1 being the student is hesitant to intervene in the situation but does not help at all, and 2 being the student was a good Samaritan and intervened during the situation. Because we did not start the experiment, we have no results. However, we do expect our results to match somewhat of what our hypothesis is. Our initial goal of this experiment was to figure out why do people do the things that they do and what is the motivation behind it. Because we do not have results, we can't really determine a lot of stuff. However, if we did have our results, we were hoping that they would help our school with developing new school policies, limit the amount of disciplinary actions, and better understand adolescent behavior, improve social interactions with peers, and also understand why are students being bullied, why is there fights and theft, and etc. Thank you.
Hello, my name is Kenneth Batiste, and I'm here to present quantifying the effect of different metals on class stability. This project was done by myself, Nicole Bassett, Ahmed Yazim, and Anna Samet. So first, I want to go over how we decided this was going to be our experiment. Obviously, our initial step was brainstorming different ideas, and from there we decided that we did not want to work with human subjects due to the extra amount of paperwork and potential unreliability. From there, we had to decide between doing an experiment with plants or blood. Now, we were told that there was an available mentor who had done research on blood clotting, so that pushed us in the direction of doing an experiment with blood clotting, since there's already a mentor who had a lot of knowledge regarding that topic. Our mentor ended up being Dr. Rob Bukowski, who is a biochemist at Augsburg University, and he had done prior research regarding the effect of zinc on blood clotting and clot stability. So, after giving us several ideas on how we might create an experiment regarding blood clotting, we decided to expand upon his original idea and add nickel and copper so that we could test their effects on blood clotting and clot stability. From there, we narrowed it down to 2 research questions: how much do certain metals bind to fibrinogen, and which metal creates the most stable clot. For each research question, we had an experimental design. Experimental design A tried to answer how much do certain metals bind to fibrinogen, and measured using a Kamasi Blue assay protein detection kit, and we were measuring the amount of unbound protein. Experimental design B tried to answer which metal creates the most stable clot, and measured using a spectrophotometer, measuring the amount of light absorbed by the clot. For methods, we used the Kamasi Blue assay, which detects unbound protein, so it was used to detect the amount of unbound fibrinogen for each metal, so that we would be able to tell how much fibrinogen was bound on each metal. Now, next we have the spectrophotometer, which shows light absorbance. So this is used to show how stable a clot was. More light that is shown through, that equals the less stable of a clot. And finally, we have a chromatography column, which rinses out all unbound proteins and used to expose the fibrinogen to the metal in a controlled way. And this way, we were able to create a model clot so that we could use a spectrophotometer. For results, this is the result for the amount of fibrinogen bound to each metal. So we have the change in absorbance, which was 0.4 for zinc, 0.1 for nickel, and 0.3 for copper. One thing to notice is that the copper did not plateau at the end. It was still increasing by the end of the 10-minute time period. And we measured using 30-minute increments. And if you can see on the zinc graph that after 10 minutes, the absorbance had plateaued. So there was no more change after the 10 minutes. But for the copper, that was not true. For our next results, we have the ultraviolet absorbance, and this measured the amount of bound fibrinogen using the spectrophotometer. One thing to keep in mind is due to the lack of exploration of testing copper binding to fibrinogen, there were some outliers in our data that we don't have an explanation for. But we can see here that nickel had the highest amount of bound fibrinogen, zinc being second, and copper being the third. So overall, we learned a lot during our project, including new techniques and how to work with the group and also professionalism. For techniques, we learned how to use chromatography columns in the Kamasi Blue assay protein detection kit, which were techniques that we had not learned before. We also learned how to delegate our tasks between each person's strengths, so that way we could efficiently complete our goals in a timely manner. And also the professionalism was another thing that we learned. We had to learn how to correspond with our mentor using proper email etiquette, and also how to work professionally in a lab space, and also the efficiency when conducting our experiments. Overall, there was a lot of things learned during this project.
Opened up my eyes, oh, and I'm seeing clear. It's finally time to leave all what's past behind me. I've made up my mind. I'm not gonna let it stop me again. Opened up my eyes, and I'm seeing clear. And now it's my time, and I'm seeing clear. It's finally here. All that I've been waiting for. It's always been near. It's in my hands and I won't let it go again. Opened up my eyes, and I'm seeing clear. Now it's my time, and I'm seeing clear.
Congratulations, seniors. As the quote says, if we could give you only one thing in life, we would give you the ability to see yourself through our eyes. Only then would you realize how special each of you are. Each and every one of you has left a lasting impact on our program, and we hope we have made an impact on your future. Best of luck to all of you. Please stay tuned for some final messages from admin and some of your teachers. Otherwise, thank you for attending the Center for Biomedical Sciences and Engineering Senior Recognition event.
Hello, Coon Rapids High School seniors and families. First, I want you to know that we continue to miss seeing all of you at our school. My heart is heavy for each and every one of you and all of your parents and loved ones that thought that we would be celebrating this accomplishment face to face. As a parent of a senior myself, I'm with you in these emotions. The coronavirus has disrupted our entire world and how we celebrate these precious and important moments for you and your family. As accomplished scientists, I know that while you understand the science, the data, and the need for us to do this celebration virtually, we are still humans that are energized by these important milestones in our lives. I hope that your 4 years in our program have been exciting, provided you with challenges, provoked and inspired your love of science and learning. With the coronavirus pandemic in the world and how our lives have changed, we can see the value of those analytical problem-solving skills, the hands-on activities, and knowledge of how our body systems work that you acquired in the program. This celebration is about your accomplishments academically for the last years in our Center for Biomedical Sciences and Engineering program at Coon Rapids High School. That completion of the culminating project of research is a mission that not only tests your knowledge, but also tests your resiliency and motivation. As a chemistry teacher myself, I know this journey is exciting, frustrating, and invigorating all at different times throughout the entire process that goes in a cycle. Parents and loved ones were also with you on this journey. Thank you to all of our parents and families for supporting your student in their journey and in their life goals. These accomplishments are about you as well, and we appreciate not just your support of your own student, but also for us as our community. Congratulations to all of you. I know that you're going to be successful graduates, and you're going to do amazing things that I'm going to read about in the future. And I want to make sure that you understand that you are welcome every single moment to come back and share those moments with us, because we want to hear about them. I am also sending you the best wishes and all the love and support from our staff, not just in the program, but throughout our entire school. You have made this school a better place to be with your leadership, with your love of learning, your school spirit, and everything that you exhibited every single day when we got to see you face to face. Please never forget that you are always a Cardinal, and you should be proud to be a Cardinal, and because we are going to be so very proud of you and your accomplishments. So again, congratulations, students and families. You did this, and we're so very excited to celebrate you today.
Congratulations, class of 2020. This is Miss Bulky. Instead of giving you a cheesy farewell speech, I thought I would just play you your graduation song instead. We're so proud of you. We're going to miss you. Best of luck in the future, and please stay in touch. Thanks.
Hooray! Hip, hip, hooray!
Congratulations! Hi seniors, it's Miss Rice. Congrats to each of you. I am so proud of your efforts and accomplishments in our program. Best of luck in your future, and please stay in touch.
Hey seniors, this is Miss Weiser.
And Miss Stevenson.
And we just want to say we are so proud of you. Congratulations.
And good luck on all your future endeavors. Go Cardinals!